Ever wondered why rainbows pop up after a storm like a secret signal in the sky? Today we're cracking the code of the rainbow, and spoiler, it's not just pretty, it's precision physics. Picture this. The sun is behind you, raindrops are ahead, and suddenly a glowing arc appears. But here's the thing that blows most minds. That rainbow exists only for you. Your friend one step to the left is seeing a different set of raindrops, a different rainbow. Wild, right? Let's zoom in on the hero of this story. A single raindrop. Sunlight looks white to us, but it is really a blend of colors. When that mixed light hits a spherical drop, three key events line up in a perfect little dance. First comes refraction. Light enters the droplet and bends because water slows it down. Then comes reflection. The light hits the back of the drop and bounces inside. Finally, the light exits with another refraction. Each bend and bounce is slightly different for each color because of dispersion, which means different wavelengths curve by different amounts. That's how white light fans out into the familiar R, O, Y, G, B, I, V spread. Now for the geometry that sets the stage. A primary rainbow forms when light inside the drop reflects once before leaving. The brightest red rays emerge about 42 degrees from the direction opposite the sun, and violet emerges around 40 degrees. That sweet spot, roughly a 42-degree cone for red, a slightly tighter cone for violet, defines where those colors can reach your eyes. Move your head, and the cone moves with you. That is why your rainbow is personal. It's a map of angles, not a physical arch hanging out in one spot. This also explains why the sun must be behind you and relatively low in the sky. If the sun climbs too high, the geometry breaks for the ground-bound part of the cone, and the bow dips below the horizon. Late afternoon, early morning, or during low sun after a shower, the angles line up and your sky turns into a giant optical instrument. If this is starting to make sense, hit subscribe for more bite-sized science every week. Let's push the story further. Why is the inside of the primary bow bright and the outside darker? Enter Alexander's band. Between the primary and the secondary rainbow, there's a dimmer region because fewer light paths from the drops send rays into that zone. And yes, there is often a secondary rainbow above the main one. That happens when the light reflects twice inside the drop before exiting. The double bounce flips the color order, so red sits on the inside and violet on the outside, and the extra reflection makes it dimmer. If the drops are especially uniform and small, you might even spot pastel, supernumerary fringes just inside the primary bow, delicate ripples caused by wave interference that ride atop our refraction story. Here's the only for you idea in a bit more depth. Imagine a cone stretching out from your eyes, its tip at your face. Every raindrop that sits on the surface of that cone and sends red light toward you helps draw the red band of your rainbow. Drops slightly closer to your line of sight feed the greener and bluer bands at their own angles. Your friend has their own cone with its own army of drops. No two observers share the exact same rainbow, even if they shout "look" at the same moment. Want a kitchen table demo? Grab a clear glass of water and a flashlight, or use a garden hose on a sunny day. Tilt the beam just right, and you'll see the colors bloom on a wall or in the mist. A prism does the same thing with a sharp edge instead of a sphere. Different shapes, same physics, refraction plus dispersion splits white into color. Bonus time. Moonbows are real. They're rainbows formed by moonlight, so they look ghostly, and often appear white to our eyes because moonlight is faint. Polarization. Sunglasses can make parts of a rainbow dim or pop because rainbow light is strongly polarized after those internal reflections. Salt water has a slightly higher refractive index than fresh water, which nudges the angles and can make the bow's radius a touch smaller. Droplet size matters too. Larger drops give you more vivid, sharply separated bands. Tiny drops smear the colors into a whiter, fog bow-like arc. And no, the pot of gold is not at the end, because there is no end. The bow is a continuous circle if you are high enough, like in an airplane, with the ground normally cutting the circle in half. So, here's your take-home map of the sky. Rainbows are a three-step story of refraction, reflection, and dispersion, drawn by geometry at about 42 degrees from the anti-solar point. The colors are separated because each wavelength takes a slightly different path. The bow is bright inside thanks to where the rays concentrate, with Alexander's band dim in between the primary and the reversed, fainter secondary. And the kicker you will never unsee. Every rainbow is personal, painted by the specific set of drops sitting on your cone of view at that exact moment. Next time the sun breaks after rain, turn your back to the light, find that magic angle, and watch physics paint the sky. If this gave you a whoa moment, share it with a friend and see if they can find their own rainbow too.